Okay, hi everyone. Today we have a new journal club. Today we have Manuel Loparco from EPFL talking about non-perturbative aspects of QFT in the sitter space. Please, Manuel, take your time and thank you again for accepting our invitation and go on.
So thanks, João, for inviting me. Yes, I'm going to talk about non-perturbative aspects of QFT in the sitter. And my talk is going to be based on these two papers, one that came out in June and one that was on the archive today. And yes, the first one is in collaboration with my supervisor, João Penedones, which of course comes from your university. And yeah, let me say that it's the first time I give a long talk, so I might mess up the rhythm completely. You can interrupt me at any time if I'm going too fast or too slow. Feel free to let me know. This is the outline of my talk. I'm going to first give a motivation, then review the geometry and unitary irreducible representations of the isometry group of the sitter. And I'm going to use that to derive a Källén-Lehmann representation. And this is here, there's going to be a natural break in the talk, because then is when I'm going to move on to discuss the paper that came out today, in which we leverage this Källén-Lehmann representation to show the positivity of some specific series expansion in a radial variable. And then I'm going to go back to the first paper and talk about the inversion formula. And again, there's a natural break also here in between, so if we don't have time, we can stop at any time in between. So let me start with a motivation. There's many reasons why one should care about quantum field theory in the sitter, and the most obvious one is that the sitter is the simplest cosmological space-time. And there is this story that quantum field theory in the early universe is a mechanism to explain the formation of large-scale structure. So the story is that all the galaxies that we see in the sky are originated from some quantum fluctuations in the early universe. But if you're not interested in cosmology, there's also other reasons, which are, for example, that the sitter is a playground for understanding quantum field theory on time-dependent backgrounds in general, and moreover, that given that the Euclidean version of the sitter is a sphere, and physics on a sphere is by nature IR finite, it's also interesting to understand that, to then learn things about QFT more in general. So what is the geometry of the sitter? The sitter can be viewed in embedding space and can be defined as a hyperboloid. So we are in R1, D plus 1, so it's D plus 2-dimensional Minkowski space, and the sitter is then defined by this constraint here. And in this plot, I also show the more familiar Euclidean Anti-de Sitter. So, and I'm going to use these big letters to indicate vectors in this embedding space. And when I use X, I mean some vector that satisfies this constraint. So it's in Euclidean Anti-de Sitter in these blue surfaces. And this orange is the sitter. And then in red, I'm also denoting the light rays in embedding space, which they're going to be useful because if you go to the boundary in Euclidean ADS or to late times in Lorentzian de Sitter, you approach the same light cone. And so in that sense, it's going to be reappearing. So these P's are, the space of light rays. So I'm identifying up to scalings this of the light rays. And here I introduce some notation, this H. So R is this characteristic length scale, and H is just the inverse. It's called the Hubble scale in the sitter. And there it's related to the cosmological constant. So I should say the sitter is the maximally symmetric solution to Einstein's equations with positive cosmological constant. Okay. And then it's important to understand that the Euclidean version of the sitter, if I look now at that constraint again, and I do a Wick rotation on the time variable in embedding space, I land on a sphere. And for later convenience, I'm introducing here a 2-point invariant, sigma. So it's the SOD plus 1,1 invariant that I can build of two vectors. And on the sphere, of course, it's normalized by the radius, by this length scale. So on the sphere is I heard a noise. So if there's any question, you can tell me. Okay.
No.
So on the sphere, this dot product can only go between -1 and 1, when the 2 points are coincident or antipodal with respect to each other. But on the sitter, instead, it takes all the real values, and from 1 to infinity, it corresponds to time-like separation, and from 1 to -infinity, it's space-like separation. And -1 is not a special configuration in the sitter. And here, there's this cut because I'm representing essentially the analytic structure of a free propagator, if you want. So there's going to be a cut at time-like separation, as usual. Okay. Okay, so now that we have the geometry, let's discuss the unitary irreducible representations. And it's important because, we start from this axiom, then the Hilbert space of quantum field theory in the sitter, we expect it to be decomposable into a direct sum of the Hilbert spaces associated to the UIRs of the isometry group, which is S to D plus 1, 1. Okay, here I'm inverting from here, but it's actually the same. It's a mistake. But in flat space, you can prove this from the Whitman axioms or from the Osterwalder-Schroeder axioms. So in axiomatic QFT, you have to choose where you start from, right? And usually you have those axioms in flat space, and then you can prove this. In the sitter, it's not well developed, the field of axiomatic QFT. So we take this as an axiom, but we expect that it should be provable from some more underlying axioms like the Whitman axioms or Osterwalder-Schroeder, the generalization of those in the sitter. So the group is the same as the Euclidean conformal group. So in particular, I have the same generators. So I'm really using the same notation as in CFT. We have dilatations, translation, but these are not now. So PI are still physical translations, right? But you should still think that it's slightly different. I'm just using the same notation, but now these are the generators in the sitter. And in particular, I can build 2 quadratic Casimirs, one for the whole group, which is the same as in CFT, and then one for the group of spatial rotations. And I will label the unitary irreducible representations by a complex number delta, which is related to the bigger Casimir. And I will say later, I will talk about it more later. And L for the SOD Casimir. Okay. So then what we want to understand is what is the resolution of the identity in this Hilbert space, right? So we need to now build up the Hilbert spaces of each UIR, and then a direct sum of those will give us the full Hilbert space. So I will just do the same thing as in CFT. I take some primary state, which I define as something that is annihilated, that is an eigenstate of the dilatation operator and is annihilated by Ki. And then I will build every other state in that multiplet by acting with translation. And now this will basically span the whole Hilbert space associated with a specific value of the quadratic Casimir delta. And here I took a scalar for simplicity. So, but the point is that a single state, delta x, is not a physical state in the sitter. It's just that if I integrate over all x's, I'm spanning the full Hilbert space associated to that value of the quadratic Casimir. So it's an abstract construction, but it still gives me a completeness relation. In particular, these states are non-normalizable in the sitter, and that's why you might have heard that delta can have complex values in the sitter. It's because even if D is is realized as a Hermitian operator on the Hilbert space, it does not have to have real eigenvalues, because when you actually in the proof of that statement, you use the normalizability of the states. So in particular for us, the delta of a primary state here will be, if it's on the principal series, is some complex number. Okay, we will consider states that carry a spin L irrep of SOD, so they're traceless symmetric in the indices, and a convenient thing that I can do, because I want to work in embedding space, is that instead of using this label X, I will use P from before, so the space of light rays, just because it's just a different label that spans the same space, right? Because we are on a D+1 dimensional surface, and then I'm identifying points on a light ray. So it's just a D-dimensional space then. Okay. Yeah.
Are you assuming something about the real part of delta? Like the real part of delta is the positive, or?
Yeah, I will tell you right now what I'm assuming, because of course, not every delta is like not every state with delta x carries a unitary irrep. And I will say now what are the conditions.
Okay.
The conditions are these ones. If we start from scalar unitary irreducible representations, then I diagonalize the Casimir, which is given, then the eigenvalue is given by this, delta times d minus delta, which is also the mass, in the sense of it's the eigenvalue of the Laplacian operator on a free propagator. And then these are the allowed values. There is a vertical line in the complex plane. These are when delta is complex, what I was saying before, and they correspond to what is called the principal series, which are fields that are more massive than the Hubble scale, essentially. And then we have the complementary series, which are real deltas in between 0 and d. And the massless, basically massless fields sit here on this orange point here. And then we have the exceptional series, type 1, which are basically tachyons with negative integer multiples of the Hubble scale. And they're still unitary irreps, but I'm going to argue later that they can actually not appear. We think that they cannot appear in the Källén-Lehmann decomposition. I will say later more about this. The point is that in the flat space limit, of course, h goes to 0 because it's the inverse radius of the sitter. So all these complementary series shrinks to a point. All these dots here, they shrink to a point. They all become massless. And then the principal series spans all the massive representations of the Poincaré group. In the spinning case, there's the only difference is that now these dots there's a finite number of them, and now the massless representations are here at the endpoints of these dots and of this exceptional series type 2. So in particular, a massless graviton is somewhere in an isolated point here, and instead a photon is at the end point here, because you put L equals 1 and you see that you get d minus 1 here. Okay, so there's lots of interesting structure, right? But for now, we're going to focus basically on this principal and complementary. Okay. Yeah, that's it. And then, so yeah, if you have questions, always just interrupt. One more thing that I should say is that in curved space-time in general, it's not unique, the choice of vacuum, right? But in the sitter, there's still a very natural choice, which is the Bunch-Davies vacuum. It's the only state that is invariant under the de Sitter isometries and satisfies the Hadamard condition, meaning that if I evaluate the expectation value on this state of a commutator of operators at space-like separation, this is 0. While on all these other alpha vacua that, if you might have heard, are other de Sitter invariant states, there you have cuts at space-like separation, so this commutator in particular doesn't vanish. But okay, there's details. If you want to ask me more, we can discuss. The point is also that this state reduces to the correct Minkowski vacuum when you go to flat space limit, and it's what you get when you do a path integral over half a sphere. So this creates this cosmological picture that you have, where you have only basically the story is that the Bunch-Davies vacuum is prepared and then it's glued to the equator, and then you have only the expanding de Sitter Lorentzian evolution. And one important aspect also is that this state is a strong quantum attractor, in the sense that if you have excitations on top of this state, they will be washed out if you wait long enough. So basically, any initial condition that is an excitation of the Bunch-Davies vacuum will look like the Bunch-Davies vacuum if you wait long enough. And so that's why it's also phenomenologically motivated. Okay, so then let me discuss 1 second about operators. We're going to consider some bulk local operators that carry some spin J irrep of S of D plus 1,1. So there's J indices, and they're symmetric traceless. And here is one physical connection with those states that I introduced before, which is that if you take a free field in the bulk and you push it to the boundary and you take the leading behavior, you get, and it acts on the bunch Davis vacuum, that's when you create those states. So this is the only connection to physics, if you want. And but I will argue later that when the field is not free, this is very problematic. When it's a general operator, what you get is something that is not an irrep, a unitary irrep. Okay, now let's say that I want to encode the spin in a convenient way, and so I will just contract the indices with some null vector that is tangential, and that's just a convenient way to represent this as a polynomial and have no indices running around.
Just a question. Here you don't have to, like usually in ADS-CFT, when you push some operator to the boundary, you usually take into account some kind of scaling.
Yes, I'm doing that implicitly. Yeah. Yes. Here I am defining this with some scaling that takes care of that. Yes.
Okay, yes. Okay.
Okay, so now we can use those ingredients to show the Källén-Lehmann representation. And how that works and what that is the following. So we built our states that are not physical, but they still span the full Hilbert space. So in particular, if I integrate over all P's, which are these light rays, right? They're just some abstract label. And I integrate over the deltas in those allowed regions, the cross, principal, complementary, etc. And I sum over all SOD spins, and I add the vacuum. This should give me the resolution of the identity over the full Hilbert space by our sorting axiom. And so if I consider, for example, a Whitman two-point function of some traceless symmetric operator, and I insert the resolution of the identity, I obtain, I carry out these integrals and I obtain the Källén-Lehmann decomposition, which looks like follows. And I'm going to now walk you through this formula. Basically here, the only thing I did is carrying out the integral over P. And the statement is that now we have some matrix elements, vacuum, operator, and then those states delta P. And the point is that those matrix elements are uniquely fixed by symmetry. Their functional dependence on the various variables is fixed by symmetry. So you can show that what you get is that you get a free propagator of some spin L field and some derivatives to match the indices that you have on the left. You have some spin J operator that will create states that have spin L from 0 to J. And so all of this blue part is fixed by kinematics. And all of the dynamics, the choice of operator and the theory and everything is encoded in this spectral density, which by unitarity needs to be positive just because it's square. It's from these matrix elements, it was the coefficient and its complex conjugate. So this is so under here I'm reminding you, what was the resolution of the identity? I just carried out the integral over P essentially, and the sum over spin is also truncated up to J, right? That's expected, and so this was the main result of our first of those two papers that I talked about. So now I'm going to instead focus on the scalar case and talk about the second paper. So if you have any questions, I will return to this at the end, but you can ask now.
Here you don't have to bother with mixed symmetry type of operators, just because.
No, I chose at the beginning to look at traceless symmetric. It's true that in that case you should look at different representations. You might have much more stuff.
Yeah, I suppose it depends also what kind of two-point functions you are studying, right?
Yes, that's true. Yeah, these are two-point functions of traceless symmetric operators. Of course, if you have a trace, you just can separate that, right? So that's not the problem. The problem is the symmetric part. If you have an antisymmetric tensor, there's something different that's going to appear on the right-hand side. Okay.
Is this analogous split representation in ADS?
Sorry, again?
Is this analogous to the split representation in ADS?
I didn't completely get it, but I think you're asking about the split representation, whether it's also there in de Sitter. And the answer is yes. You have to be careful about light cone singularities, but indeed here we are using that basically. Those matrix elements are like bulk to boundary propagators, and then you can you carry out the integral over P, you get the full bulk to bulk propagator, which continues to the harmonic function in ADS. I will point that out later. Okay. So now I'm going to have an intermezzo about the second paper, and then I'll go back to the first one. Basically, let's focus on the scalar case. So now we're looking at a two-point function of a scalar operator, and I'm writing the Källén-Lehmann decomposition. And here by P plus C, I mean principal plus complementary. And we have a strong conjecture in our paper, which is that actually scalar operators cannot contain those exceptional series type contributions. And the main reason is that you can show that each contribution would have cuts at space-like separation. But at the same time, each contribution has a different sign in front of that singularity. So you might expect that there's some very complicated operator that creates such irreps on the exceptional series with different weights such that the singularity vanishes. But in all the examples in which we've computed the spectral density, weak coupling, strong coupling, CFTs, and free theories, they never appear. So that's still a conjecture, but okay. So let's take it as a starting point, and let's think about this two-point function on the Euclidean sphere. So we are looking at some QFT on the sphere that we are in our mind. We keep that it will continue to some unitary QFT in de Sitter, and so it should have this sort of Källén-Lehmann decomposition. So let's take this as a starting point, and then we notice the following fact, that this is how the free propagator of a massive field looks like, and a massive scalar. And on the left, I'm showing again the analytic structure. And the point is that if I introduce this invertible map between sigma, which was, remember, it was the dot product in embedding space, and rho, then this is the new variable that we introduced. Then you're mapping the full complex plane of sigma to a unit disk, where the cut is now a circumference. And this is the usual radial variable. It's the same change of variables that is used in conformal bootstrap and S-matrix bootstrap. But it buys us something really interesting, which we don't completely understand what is the interpretation, which is the following fact, that when you do this, when you do a series expansion of your free two-point function in this variable, you get that the stuff in front is all positive coefficients. And we initially noticed that numerically, and then we managed to prove it analytically, but it's quite involved to try to do that. And it seems to be, well, it's a fact that these coefficients are all positive. There is no physical reason why, so actually any idea is welcome to explain that. But the point is that now we can use this fact to derive a number of other consequences, and one of them is analyticity, because if you have that this sum is positive, then you can bound the absolute value of any two-point function non-perturbatively in terms of its absolute value. And then you shrink that absolute value. You can put it inside the integral. The spectral densities are positive by assumption. We're looking at some unitary two-point function. We prove that these coefficients are positive, so the absolute value ends up on rho. But when you do that, you are on the sphere, because you see the values of sigma between -1 and 1, which are associated to two-point configurations on the sphere, are mapped to rho between 0 and 1. So that means that wherever you are in complexified de Sitter space, the two-point function is bounded by the two-point function on the sphere. So if you assume that the theory on the sphere is finite, then you have analyticity in the full complexified domain. So there's this bound that one can write. And
can you go back to the function g of delta? So that f is a 2f1?
Yes, sorry, it's a regularized hypergeometric, yeah.
Yeah, and is that the block of a BCFT, a boundary CFT? Or?
Sorry, again?
Is that somehow related to the conformal block of boundary CFT?
It's related to the conformal block of a CFT1, if you want, and we use that to prove positivity. It's something that we need to use in our proof, but it's like a conformal block of 4 scalars with complex dimensions. So then you cannot, you see, it doesn't follow just from the unitarity of CFT1. It still happens to be positive, the radial expansion, but it's not obvious that why. It's also what I was saying before, it's also the harmonic function, this one. So if you want, if you look at this as some continuation of the 2-point function in ADS, then this is the eigenfunction of the Laplacian that doesn't have singularity at coincident point in ADS. It's the harmonic function.
Oh, okay.
So this proves analyticity, but moreover, it also tells you that any 2-point function non-perturbatively will have a series expansion with positive coefficients, where now these coefficients are given by the integral of the spectral density against the coefficients of the free scalar. And so this is like a much easier consistency condition to have on 2-point functions that one can check or impose in a possible bootstrap setup on 2-point functions.
No, sorry to interrupt again. Can you just say in a little bit more detail why that bound proves analyticity? I don't think I understood.
So the starting assumption is that the 2-point function is finite on the sphere. This bound, yes. First of all, do you agree that this bound tells me that the 2-point function anywhere in complex rho is bounded by the 2-point function on the sphere? Maybe that's the point that I didn't convey, because the point is that basically when you take the absolute value of rho, wherever you are in the unit disk, you take the absolute value, you land on this line between 0 and 1, which is exactly mapped to the 2-point configurations on the sphere.
Yeah.
You see? And since I'm bounding it everywhere else in the disk, equivalently everywhere else in this plane, by the values it takes on the sphere, if my starting assumption is that the Euclidean theory is well-defined, the one that I compute with Euclidean path integrals, right? That it's well-defined and finite, then this shows that everywhere else in complexified de Sitter. So the point is that every Wick rotation that I can take from the sphere to go to, I don't know, some time-like separation in de Sitter or some other space-like separation in de Sitter, all the paths of the Wick rotation are within this analyticity domain.
Okay.
Another word, the definition of analyticity is that you have a series expansion, right, of the function, and that's maybe, if you want to, you see it better from here. I write a series expansion around the origin. This covers the whole unit disk, covers the whole complexified de Sitter space, and so then that's analyticity, the definition, if you want.
Yeah, I see. Okay, I understood. Thanks.
Welcome. Yes, and then some more technical detail is that this sum converges very fast. Well, depends on where you are in the 2-point function, but it converges as rho to the n and to the alpha. So if you have in this example, I'm showing a 2-point function of a CFT in the bulk of de Sitter, and I compute it and I do a series expansion in rho, and then I show that while it doesn't work here on the left, when you go to infinite space-like separation, it starts breaking down. On the right, it converges quite well, and these are the residuals as a function of rho, and for fixed rho, you can see here that the relative error decreases exponentially fast. Okay, so this is another natural cutoff. If you guys have more questions, I can pause here. Otherwise, I go on. So now I'm going to talk about the inversion formula, or how to compute the spectral densities. So basically, now that we proved analyticity, yes, an important point is that basically 2-point configurations in ADS, at least if you are continuing the Whitman function in the way that it's done usually in the literature, will land you always in sigma between -1 and -infinity. And you know that from ADS, probably that's the range of that this 2-point invariant takes. And so in particular, so we can do that continuation to ADS. And what we land on is a harmonic decomposition. So because if you take literally that 2-point function I showed you before, and you continue, as I was saying before, you get the harmonic function. And the particular continuation that is done is usually that you take these 2 points, not necessarily at equal times, and you continue them on one branch of the Euclidean ADS and on the other. And that's, by the way, why you obtain the harmonic function that is not singular coincident points, because these 2 points will never touch now. And the point is that these harmonic functions on the principal series, they are an orthogonal and complete basis of square integrable 2-point functions in Euclidean ADS. And so that means one thing, that let's say someone hands me a 2-point function in de Sitter, I continue it to ADS, and then I check whether it's square integrable or not. If it's square integrable, then that means that the original 2-point function in de Sitter only had principal series states, because this is a complete basis. So this gives a criterion to understand already immediately what's the content of the Källén-Lehmann decomposition going to be. But moreover, because they are orthogonal, I can just convolve the 2-point function against a harmonic function, and I will extract the spectral density over the principal series. Now, let's say that then, yeah, okay, I can talk about more about how to derive contributions of the complementary series. And the way that it works is that if you have a 2-point function and you have some parameter that you can tune, for example, take a CFT in the bulk, and you have a scaling dimension that you can tune, you can see that for some values of the scaling dimension, you have a square integrable function. And so then you apply the inversion formula and calculate the spectral densities over the principal series. And then you can continue that scaling dimension until the 2-point function is not square integrable anymore. And what you see is that what will happen is that some poles in the complex plane of delta of the spectral density will cross the integration contour, and they will always lead to then new irreps in the complementary series. So that's how in all the examples the complementary series appears. And okay, so this was known before, but what we did in our paper was just generalizing it to any spin. And I'm not showing you the formula because it's a bit ugly. Okay, now let's talk again about boundary operators. The point is that now that we have the Källén-Lehmann decomposition, this is already a decomposition in the spectrum of the theory. In ADS, the spectrum is discrete, so you expect a sum, right? And so in ADS, what is usually done is that you have this integral just because of the functional analysis, there are complete bases, and then this integral is closed to one side, and it becomes a sum over the poles, and those poles are the spectrum because they are related to the CFT states, but to the CFT operators. In ADS, in de Sitter, that's not the case. So the poles in general are in some random complex positions that are away from the unitary irreducible representations. So yes, you can still close the contour and get some and go to late times, and you get some CFT 2-point functions, Euclidean CFT 2-point function, in the sense that they satisfy all the isometries, but the scaling dimensions will all be complex numbers, not even on the principal series. And moreover, there is a puzzle here, because this sum that you get over boundary operators you cannot truncate it at any point, because if you think about it, our Hilbert space, we constructed it with CFT states with scaling dimensions on the principal or complementary series or exception or whatever, the unitary reps, and now none of these are actually what you get from these boundary operators, right? These boundary operators now acting on the vacuum will create some CFT states that are orthogonal to everything in the Hilbert space. So if you do this sum and you insert the resolution of the identity, you get naively you get 0. And this is a bit of a puzzle that is, there's no clear resolution to. So something interesting to think about.
So just a question.
Yeah.
Isn't your second bullet point way to identify the spectrum? Like, can't you play the game the other way around, where you first have the correlation function and then the spectrum of the theory from that correlation function?
I didn't understand. I cannot hear really well.
Sorry, it's easier. Can't you usually just read the spectrum from the second equation you have written there? Like, isn't that the way of getting the spectrum of the theory?
That's how you do it in ADS, right? Because what you get are the unitary irreps on as a sum. But now my states are in the principal series. The spectrum is the support of the Källén-Lehmann decomposition here. I cannot learn anything. When I do this decomposition, I get some complex delta stars that are not part of the spectrum. They are the spectrum of boundary operators of the CFT that I obtain, but they have nothing to do with the spectrum of the Hilbert space of the QFT in the bulk of the sitter.
Well, but do you mean that because they are not unitary representations, or?
Yes, yes, and there's no, yeah.
Okay, but in some sense, if the theory was non-unitary, would that be a reasonable spectrum?
Again?
If the theory was non-unitary, will these delta stars be a reasonable spectrum for the theory?
It depends on what you mean, because they are the spectrum, if you want, of this Euclidean CFT on the boundary, but it's not the spectrum of the theory in the bulk, because there's no bulk state boundary operator correspondence in the sitter.
Okay. Okay, I see.
I think you're applying intuition from ADS, but it doesn't apply here.
Okay.
Okay. Okay, well, actually, okay, I can mention something since we're not super tight on time right now. I can mention that there is one case in which there's some connection between these boundary operators and physics, which is if you consider the physics in the static patch of the sitter, which is the patch that is covered, it's the patch that is in causal contact with an observer that is free falling in the sitter. I don't know if you've ever seen the Penrose diagram of the sitter. It's a box with two diagonals, and you look at the triangle on the right, then that's the static patch. And then these delta stars are related to the quasi-normal modes at the horizon. So, and they are related also to the eigenvalues of the Hamiltonian in the static patch, which you can define there. There's a time-like killing vector. It's not globally defined, but you can define it in the static patch. So it's related to the spectrum only in that case.
Thanks.
Okay, so here I'm just summarizing some checks we did. We computed the spectral densities in a bunch of cases. So we took, for example, here a composite operator made of a free vector and a free scalar. And here what you see is exactly that we can match the things that are known from group theory. From group theory, we know how a multi-particle state made of a vector and a scalar decomposes into unitary irreps, and we find exactly the same structure in the Källén-Lehmann decomposition of this operator. And then we checked some CFT primaries in the bulk of the sitter, spin 0, 1, 2, some a conserved current in scalar QED. This is unpublished work, though these last two are still unpublished. And then stress tensor of a free massive boson. Okay. So let me conclude and list a bit of open questions that remain. Yeah, so right, the motivation stands. All these facts about QFT in the sitter are relevant to cosmology and to understanding quantum field theories on the sphere, which are by nature IR finite. And we have some upcoming work on understanding RG flows and some rules. But some open questions remain, such as, and we don't know exactly how these exceptional UIRs can appear in the Källén-Lehmann decomposition, so in particular massless gauge fields. We still don't know, haven't worked out how that those can appear. There is this puzzle that I mentioned, when you insert the resolution of the identity in any term in that sum over boundary operators, and you get 0 naively, which is not what you have on the left-hand side. So this is an interesting question. And then yes, there's this. We're lacking an interpretation for what is the physics behind, why is the expansion over this radial variable with positive coefficients. There is no physical reason why it should be the case, but it happens to be. That's it. I have one more slide with some practical example if you were interested, or we can.
Yeah, I think we have time, so
okay.
Go on.
So this is a concrete example of what happens in a specific case. So let's consider a theory of a free massive scalar phi. Then clearly, if I do the Källén-Lehmann decomposition of the operator phi, I will get a delta function because it's already a unitary rep. I didn't write it here, but if you regularize this delta function, you get 2 poles in the complex delta plane, and so what you see already is that there's going to be 2 boundary operators, boundary primary CFT operators related to one bulk scalar field. Okay, so that's the case for if you just look at the operator phi. But more interestingly, let's look at the operator phi square. Then there's going to be a continuum of states. The first thing you do is you take this 2-point function, you continue it to ADS, and you check if it's square integrable. And what you find is that it's square integrable only if this condition applies, which is a subset. If you want, all of the principal series satisfies this, because the real part of delta there is d over 2. And then a subset of the complementary series also applies. So in those 2 cases, the principal series will be enough. So let's say we tune delta phi such that this criteria applies. Then we apply the inversion formula, and we can calculate the spectral density. It's some product of gamma functions, usually. And all these gamma functions show poles precisely what you would expect from CFT, essentially, given that we had those 2 scaling dimensions, delta phi and d minus delta phi. Those are what you get by taking one bulk field to the boundary. Now you get all the double traces that you can form from those. So you get 2 delta phi plus 2n, but you get also 2 delta phi bar plus 2n. So bar is just d minus delta phi. And then you get d plus 2n, which are the double traces made of delta of O delta and O d minus delta, which sum up to d. And then you can continue delta phi beyond the threshold, beyond this condition here. So it's not square integrable anymore. And you see that a bunch of poles start appearing, all with real delta. So they all these deltas, basically, as you shift all these poles, as you shift delta phi to the complementary series beyond this thing, they are all real, because you have delta phi, d minus delta phi, these are all real numbers. And so they appear as irreps within the complementary series. And it seems to be a very general feature, also in CFTs, and there's some strongly coupled case in the literature as well, in the ON model. So they do large N, but strongly coupled. And they also see the same effect. It seems that there's no example in which the complementary series appears as a continuum, as in principle it could, though, like from the arguments I showed you. And then what we did in our paper, among other things, is we turned on some phi-4 interaction. And then what you can do is you see that these poles in row shift with the interaction, and they introduce some anomalous dimensions to these operators. But again, these operators, there are some, it's difficult to give them a physical interpretation.
Okay, very nice. If you have finished, then let's thank Manuel first. And now we have time for questions. Any questions here?
Yeah, I have a question. It's not strictly related to what you explained. In the beginning, you said that you are assuming that the Hilbert space can be decomposed into unitary irreducible representations of the symmetry that I expect my Hamiltonian to have. How could that? Do you have any idea or any example or any intuition?
It's not the symmetries of the Hamiltonian. There's no Hamiltonian, by the way, in the sitter, right? There's no global Hamiltonian because there's no global time like Källén vector. But they are the isometries of the metric, if you want, or of the global metric. So as I mentioned, in flat space, you can prove that from the start, from like Osterwalder-Schroeder axioms or Whitman axioms. It's difficult to, you want an intuition of why that should be true.
Or example of how it can fail, or like is it there any known example where things like this fail?
Yes, there are non-unitary QFT. Usually it's non-unitary QFTs, but there's some non-unitary QFTs, CFTs, which violate this this assumption, but they're non-unitary. So they of course, you know, once you're Euclidean, you don't have to have unitarity. You can have some perfectly fine like statistical physics model that doesn't continue to a unitary QFT. And so then in that case, you don't have this decomposition anymore. But otherwise, there's no known counterexamples.
Okay.
Yeah.
So you say it like an axiom, but you can just say like, I'm just interested in theories that respect this. Like I'm interested in unitary theories that should, in principle.
Yeah, but yeah, I guess. So Jashin, one of my collaborators, is from the community of axiomatic QFT. And then if you say, you know, you have to be very careful about what are your axioms. And and you see there, as I said, like there's really like a rigorous way to prove it from the well accepted axioms of flat space QFT. And in the sitter, there's a hope that it's also possible. So there's a community also that is trying to do this in the sitter. So Bros, Epstein, Moschella, these people were pioneers in axiomatic QFT in the sitter, and they have some proposals, but they always seem to have to add one more axioms than the ones that you have from Osterwalder-Schroeder in flat space to get to the Källén-Lehmann decomposition, which is basically equivalent to saying the decomposition of the Hilbert space is possible.
If people consider like a flat space limit of ds, starting with a given set of axioms, and see if those are related with Whiteman axioms or Osterwalder-Schroeder axioms.
So one thing that we did is also show the flat space limit of this Källén-Lehmann decomposition. You land on the right Källén-Lehmann decomposition in Minkowski space. So yeah, I would say, I mean, it's proven that if you take a flat space limit of any well, I don't think there's in-depth work on that, no, but it's expected to be true. Yeah.
Any other question? Have you, I don't know, probably you have tried this many times, but is there why can you not relate like this choice of radial expansion of radial coordinate to, like in CFT, this is related with some choice of configuration. Here, that idea cannot be used. Why exactly?
So you're saying in CFT, it's some like choice of configuration.
Are in a given position related with OPE starts to fail, right? And then we just say, okay, but I have conformal symmetry, I can choose some frame, and then I know where the cuts can start. And then you can relate this configuration with another configuration which has like reflection positivity, and then it's clear that the coefficient should be positive. Here, that idea doesn't work exactly. Why?
Right, but I think that you're using also the OPE, right? And there you have a 4-point function.
Yeah,
which then you use these OPEs and you're using the positive inner products. But here it's a 2-point function. And okay, let's say that I want to relate it to a problem in CFT. As I was saying before, you look at the 4-point function you read off what are the operators in your 4-point function that match this thing that looks like a conformal block. What you get is some operators with complex dimensions. They are not in the principal series in particular. There are some other point. And so there's no argument from the CFT alone that tells you that this should be, that this expansion should still be positive as it is when the deltas are real.
Yes, yes. And perhaps I'm assuming a little bit more about OP convergence in this case, that it's not true.
Yeah, but this is already a 2-point function also, right? So yeah,
yes, I agree.
No.
More questions? Here, not at home. I don't know. Okay, if not, let's thank Manuel once again.
Thank you.
And we can stop here. Thank you, Manuel. Very nice talk.
Thank you. Ciao.
Thank you.
Ciao. See you.
See you tomorrow.